Okay, good morning, all of you. Today we are going to see the unconstrained and constrained optimization. Before that, recapping previous class, that is a classification of optimization problem. As we discussed, there is a different classifications elaborately with different equations and all, and linear programming, integer programming, and quadratic programming, non-linear programming, and stochastic programming, dynamic programming. Like this, in the last class, I elaborately explained different classifications of optimization problem. In that, there is a single objective optimization problem, multi-objective optimization problem. Like that also we discussed. In the single objective optimization problem, only one objective function will be there, and we can able to optimize that objective function. In multi-objective optimization, we have more than two objectives. You need to optimize at a time. For that, we have different mm, methods. We have that is what we call it as ఇది ఇరిగింది హ్యాండ్ ఇలా ఊనుకుంటే ఇది సర్లే తర్వాత like that we have different optimization problems. That is a single objective and multi-objective optimization. That also we discussed. And one is we call it as there is a e-constraint problem, and then we can weightage mechanism f1 plus f2. Some must be one weightage like that, 0.2 f1 plus 0.8 f2, like that. We can able to get the problem optimization using single objective as well as the multi-objective optimization. That is the one of the method we may have. So another one, now today's class, we can see the unconstrained optimization and constrained optimization. In that unconstrained optimization, meaning of this unconstrained optimization, if any objective function is there, subjected to some constraints, we can incorporate. Because suppose one normal example, subject marks. Let it be, you need to get the 40 marks to pass the subject. The 40 marks we required to pass the subject. But in that, without any constraint, that we call it as unconstrained. So straight away, 40 marks, CAE and then SCE together, if you get 40 percentage of marks, you will pass. So here there is no constraint. Whether you can get here full marks and suppose here 30 marks, here 10 marks, also you will pass, or maybe here 20 marks also will pass, like this. So this is the unconstrained way. But there is a constraint in that. What is the constraint problem means total 40 percentage of marks you need to get. I mean, let it be out of 100, you need to score 40 marks. But there is a constraint, you must secure 40 percentage of marks in external. It is a mandatory. That is a constraint. Suppose let it be as a external is a 60 marks, then what you can do is 40 percentage of marks you need to secure. That means minimum 24 you must get in the SCE to get the pass. This we call it as a constraint problem. So normally, objective is to pass the subject. Object is subject, so you need to score 40 marks. But no constraint, then you can get internal 40, external 60 pattern. In that, if you get only internal 40. If you score directly 40 marks here, and external you must attend the exam and you scored the 0 marks, then also you will pass. If it is a unconstrained. Constrained means even if you score internal 40 out of 40, but external must secure 24 marks. If it is a 40 percentage of that, in that we call it as a constraint problem. This is the broadly to understand what is the constrained optimization and unconstrained optimization. You can see that an unconstrained optimization problem is one where you have only have to be concentrate in the objective function alone. So we are not concentrating the constraints because no constraints here, the subjected to the constraints is not there. It may be some other problems. We may have many number of constraints as well, but here we may have only one objective. That objective are try to optimize. That is only the problem here. The function that you are trying to optimize, uh, in that case, no one of the variable in the objective function are constrained. Suppose f of x is there, or f of xi, let us assume that the function consisting of x1 plus x2 and so on, x3, let us assume that we are not giving any constraint of x1, let it be 0 less than or equal to x1 less than or equal to 5, or 3 less than or equal to x2 less than or equal to 10. Like that, if you not mention anything, whatever the value you can get it here, with minimizing the function, that we call it as a unconstrained the optimization problem. That what I mentioned, no one of the variable is having as a constraint. So in that, now we can see that whether the function is a minimization or a maximization. Second order condition for a maximization problem, what we can identify whether the function is maximization or a minimization, like that. We can see here first order condition for maximum at a point x star, f of x1, when f star is equal to 0. Suppose if any equation is there, we just differentiate with respect to x, that is equal to 0. And the second order condition for maximum point at x star and the function, when f double dash, that means f double dash at x star is equal to condition, x star is less than or equal to 0, means f double dash means differentiation two times we have to do it. First differentiation, then second order differentiation, it is less than 0. That means it is a negative. Similarly, if the problem is a minimization problem, we can observe that as usual, f dash is equal to 0, but f double dash must be greater than or equal to 0. That is what second order condition, minimum at point x star and the function is when f double dash, the second order differential equation greater than or equal to 0. And example we can see is in first order, the second order conditions. Suppose you have the equation x cube minus 6x square plus 9x. Then the first order condition, what I can write, f dash of x that is equal to 3x square minus 12x plus 9. So like that, you can easily and equate it to 0. That is for the first order differential equation. You can write it as a 3x square minus 12x plus 9, that is equal to 0. That implies we can notice the points x is equal to 1. If I put x is equal to 1 here, what I can get 3, then minus 12 plus 9. So that value is equal to 0. Similarly, x is equal to 3, you can put it 3 into 3 square minus 12 into 3 plus 9. So these are the points we can satisfy that condition. The next step is to determine whether the critical point or maximum or a minimum. How we can find that critical point is maximum or a minimum? As per the previous slide, there is a differentiation. One is x dash. I mean, first order differential is equal to 0 and second order differential equated to negative for maximum, positive for minimum. In that aspect, you can see this point. The next step is to determine whether the critical point is maximum or a minimum. In that case, these can be found by using the second order equation. So now what you can do, f double dash, you can do it. If I do x double dash, then 6x minus 12. Then take common of 6, then it will be 6 of x minus 2. In that, if I keep x value is 1, what can happen? There is a minus 6, that is less than 0. As per our previous slide, as I mentioned, f double dash of x star is less than 0, then I can say it is a maximum, or f double dash x star is greater than 0, that I call it as a minimum. So in that aspect, we can easily find there is a minimization problem or a maximization problem. After calculating f double dash, that means the second order differential equation, we got the value minus 6, therefore it is a maximization. Similarly, another point we noticed to satisfy that equation, one is x is equal to 1 and x is equal to 3. Now keep x is equal to 3 and we noticed that 6, we got it double dash of x is 6, then it is a minimization problem. So from that, if want a maximum value, keep it x is equal to 1, the function value we can easily obtain, and then x is equal to 3, we have a minimum value. So now we'll go for another one, that is a constrained optimization. In the previous slide, we discussed unconstrained problem. In that case, whatever values we are getting, we don't want to bother about it. Only our constraint or our problem is to minimize the function, not anything. But now, what we can do is, and there is a constrained optimization. In the constrained optimization, what we can get it as a each variable they have as a limitation. Like that, let for example a power system problem, cost function is one equation. In that generator 1, generator 2, all these things we have to sum it of generation cost, will get the total cost. But generator 1, the generation limits are there, generator 2 limits are different, like that. We need to satisfy that limits to get it as a final objective function minimization problem. In that aspect, constraints need to be considered. Normally, unconstrained problem is not much useful anything. We need to consider only constraint problem. Is occur when one or more, means optimization will occur one or more of the variables in the objective function is constrained by some function. Like, as I said earlier, f of x may have x1 square plus x2 square, then you must know something constraint x1, something 0 to 10, then x2 maybe minus 10 to plus 10. Like that, if I have the function problem or a problem statement is like this, then I can say it is a constraint problem. In that, we have the objective function and set to the constraint. We'll see the maximize to be set up the following. Let maximize the objective function f of x with respect to x, given a set of constraints g of x is equal to c. Again, constraints, we have two types of constraints. One constraint is a what you call it as equality constraint, and the other constraint is a inequality constraint. Suppose our function x1 square plus x2 square, one constraint may be x1 plus x2 is equal to something 100. Let us assume that. Other constraint may be x1, let it may be some 30 to 50, anything. This is the inequality constraint, and this one is the equality constraint. The any problem, it has to meet these constraints to get as our final optimal value or objective function value. So in that aspect, we can consider there is a subjected to the constraints as well. So one maybe what we call it as equality constraint. Another is a inequality constraint. So both need to satisfy while we are solving the problem somehow. That's what, for example, I mentioned like this. There is a what you call it as a function. It may be maximization or maybe minimization. Anything is fine. The maximum of f of x subjected to g of x is equal to c, and example of constraint optimization problem. Then you can see that f of x is equal to 5x minus x square something, and subjected to the constraint x is equal to 2. Then what we can write, x is 2 means that is a constraint. The answer to this problem, x star is equal to 2. Similarly, constraint optimization with two variables may be there in the one variable. Now we can consider when you are trying to maximize, can be set up the following equation. There is f of x consisting of x1 and x2 variables are xi, x1, x2 like that. Then constraints are g of x1 comma x2 is equal to c, something maybe g of function consisting of two variables that must be equal to some value, some constant value. Like that, the function is there. With respect to x1 and x2, there is a function that is whether we are going to maximize or a minimize, and subjected to another equation that is equal to c constant. And we can observe the function x1 into x2. With respect to x1 and x2, they also mention the value x1 plus 2x2 must be equal to 600. This is the what you call it as a value. Now, to solve this problem, we can observe the converted into unconstrained problem. Normally, in all power system problem, maximum extent there is a constraint problems only. In a constraint problem, we need to convert that unconstrained problem to constraint problem, because directly we can, it is not possible to solve unconstrained problem. That is the reason this problem is a constraint problem. In this constraint problem, we need to convert the constraint problem to unconstrained problem. So if we solve the constraints of x1 as a function of x2, then I can write this equation. Anything will be like this. Because total is a 600, that is equal to x1 plus 2x2. From that, I can write x1 is equal to 600 minus 2x2. Now, x1 into the objective function gives the following new unconstrained problem. Because when this is unconstrained, this you can substitute it in a equation with respect to only one variable, then automatically these constraints are incorporated in the problem, and whatever solution we are getting, that you can say is a unconstrained problem only. Now the question arises, now if it is a small one or two variables, we can do it like that. But it's a big power system problem, nonlinear problem, so that is a little bit difficult to manage the things. Now, We can see that's what you mentioned here, wherever the variable x1 is there, because our function is x1 into x2, because f is given, f of x1 comma x2, that is equal to x1 x2. Now they mention 600 is equal to something, what you can say the problem, x1 plus 2x2. So the 600 is nothing but a x1 plus 2x2. Now I replaced wherever the x1 is there here, with this. So therefore f of x1 comma x2, that is equal to 600 minus 2x2 into x2. So in that case, we can solve the problem as well. From that, we got it x2 star is 150, and which implies x1 is equal to 300, because once if you know x2 is 150, as per our equation, x1 is equal to 600 minus 2x2, then put it here, then we'll get it as a x1 value, that is equal to 300. Now, in the this problem, what I mentioned in the previous one, f of x1 into x2, we made substitution to turn the constraint problem into unconstrained problem. That's what we did for this problem. But if we have more number of variables and more number of constraints, this method is not suit. That's what I mentioned here. There is a we have multiple constraints, then this is a difficult or impossible, because in a power system problem, many number of control variables are there in a function, and each variable may have different constraints in the each variable. So all together will not incorporate in a function to get our solution. Then that is what we are going for as a Lagrangian method. This is the very famous method in the problem Lagrangian multiplier, or what you can say. Using the Lagrangian multiplier, we are able to solve the problem. In that case, we can see here, lambda or any variable Lagrangian multiplier, you can use it. This Lagrangian multiplier lambda to transform constraint problem to unconstrained problem. So now, instead of substituting these variables there and minimizing or maximizing the problem, how many constraints are there? Everything you can incorporate it into, or converting into, what you call it as, equality, or constraints into inequality problem, inequality constraint. So this is a, what we call it as a, or, unconstrained problem to constrained problem. That we can see that whatever function, this is equality constraint, we make use of this Lagrangian multiplier. So whatever the function is, variables are, let assume the two variables. Third variable you can incorporate or a Lagrangian multiplier x1, x2, and then lambda. We can see that function f of x1 comma x2 plus Lagrangian multiplier, then subjected to the constraint g of x1 comma x2 minus c, because our equality constraint is mentioned, x1 x2 some equation must be equal to c. Then from this I can write x1 comma x2 minus c. This is your constraint. So now you make use of a lambda Lagrangian multiplier, and you can get it as a our function. If it is a maximization, suppose if it is a minimization, what we can use it, c minus of this, we can get it as a minimization function. So this is the way we can easily use the constraint optimization, and unconstrained case, we are converting constrained problem to unconstrained problem. Now it is one equation. So whether it is minimization or a maximization, using that problem, we can easily solve our normal problem. Now it become as an unconstrained problem. So in that case, we need to optimize the variables. So apart from the x1 and x2, now lambda also come into the picture. In this equation, using the first or second order condition, now whatever problem we discussed in the previous one method, converting this x2 variable or x1 x2, in that we are replacing now that process. Instead of that, we make use of a Lagrangian multiplier. For that, Lagrangian function is there. Now first order condition, how many variables? Here three variables are there, and you can just differentiate it three variables, and we can easily get this. So this is the mm, way I can differentiate. First one is with respect to x1, you can differentiate, and then with respect to x2, and with respect to lambda, and we can easily get your equation. So three equations are there, and three unknowns, we can easily solve it. That is what the unconstrained and constrained problem. So now they may ask you write a short note or explain constrained and unconstrained problems. We can elaborately explain these analysis. And in the constraint problem, what you can write straight away, constraint problem is not possible to solve. In that case, there is a conversion constraint problem to unconstrained, or you can use Lagrangian multiplier. That function is going to do means constraint to unconstrained using Lagrangian multiplier. Another one is a optimality. So here all the objective functions, we are going to identify there is a optimal value or x star, whatever you call it, whether it is a local optima or a global optima. So in a local optima, in each iteration, which one is in that particular case, the smallest value is a local optima. In terms of example of class marks or class ranks or anything. So who is the topper? That percentage we call it as a global optima, and individual percentage we call it as a local optima. That is the analogy in simple understanding way. Local optima is a minimization. You can see smallest function value in the neighborhood, that we call it as a local optima. There can be multiple local optima also, because many smallest values are there. In each case, we will get it that. Whereas global optima, what we can do is smallest function value in the feasible region, means final optimal value. I call it as, now we can see the optimization problem or minimization problem is mentioned here. I want to know what is your minimum function value. So in that case, we can observe that the lowest value is your minimum optimal value. So this is the way we can able to get the minimum function value. Similarly, these are also minimum values only, but it is a local minimum. But we will compare to all globally, this minimum is your final minimum, that we call it as a global optimum. Now there is some points we will discuss small problems, how we can identify as a minimization or a maximization, like that. Stationary point also will be there for a continuous and differentiable function is to be x star. F dash is 0, that means x is equal to x star. So what is x star belongs to domain of definition, and the stationary point may be as a minimum or a maximum or a inflection point. So this is the one point you can remember, inflection point. Suppose as per this diagram graph, you can notice that smooth plane curve at which the curve turns changes sign. You can see it is a one smooth curve. From this point onwards, it changes the sign. This will go to positive, this go to negative. That point we call it as a inflection points. So in that we can see there is a inflection point. From this it is going down, from this it is going up. And minimization, the point which is the lowest point, we call it as a minimization, that is f dash is equal to 0 point, or maximization f dash is equal to 0 in the upper side maximum value peak, that I call it as a maximization problem. Now for example, you can see f of x is equal to x square plus 3x minus 5. And what we need to do is state if the function attains a maximum or a minimum. So if you understand previous slide, then we can easily say whether it is a maximum value or a minimum value will obtain, because there is a two things I mentioned: f dash of x is equal to 0 and f double dash of x is less than 0 one case and greater than 0 other case. Less than 0 is maximization problem, greater than 0 is a minimization problem. In that case, first f dash of x we calculated. What we got? 2x plus 3, that is equal to 0. We have to do that for whether it is a maximization or a minimization. First differential equation is equal to 0. That one will be the fixed one. And from that, what you got? First differentiation, if we do, that is a 2x plus 3, that is equal to 0. From this, x is equal to minus 3 by 2. That is the case of first differential equation. And again, if you do second differential equation, f double dash, that is equal to 2. We got it. Now, whether it is a positive or a negative. So based on that, we can easily identify whether it is a minimum value or a maximum value. So it is a x less than 0 f double dash is less than 0 means it is a maximization, and greater than 0 means it is a minimization. So it is a greater than 0. In that case we can write this one is a minimization problem. That's what x star we already calculated minus 3 by 2, because the first differential equation case. Now this x star value minus 3 by 2 substituted into f of x star, then we'll get it as a value, that is your minimization value, or a minimum value is minus 29 by 4. That we call it as a minimum function value. It is easy to find first differential equation and equate it to 0 will get as optimal point. And second differential equation, you can able to identify whether maximum value or a minimum value, and the x star point to substitute it into function, then we'll get it as a minimum or a maximum. Same thing. Another problem, what they asked is function is given x minus 2 power 4, and also state if the function attains a maximum or a minimum. In that case, f dash of x, we can do it, that is equal to 0. From that, x star is got it as a 2. Now, at the first differential equation, we cannot identify whether it is a maximum or a minimum. But second differential equation, if we do, then we can easily identify the function value as well. And here we got it as a positive, and n is even number, because power n also you can make it x star is 2 point of minimum, and function attains the minimum value of 0 at this point. So after doing this, we came to notice that the function value is equal to 0, because x star is 2 and 2 minus 2 power 4, that anyhow is a 0. And third problem, we can see f of x is given something, and classify the stationary points as a maxima or a minimum point or a point of inflection. So what is point of inflection? From that point onwards, the sign is going to change. Now we can see f dash, we did it as per our same scenario. X power 4 minus 3x cube plus 2x square is equal to 0. From that, you'll get that some points x star is 0, and you can check it with probable roots for this. and x double dash star, we got it as a something 0. And if I keep some other triple dash, then that we got it as a 240. And for all the cases, we substituted the optimal value x star is equal to 0. And since the third derivative is non-zero, then neither a point of maximum or minima, but is a point of inflection. So like that, we can identify with different cases, because how many cases we have: x is 0, x is 1, x is 2, like that. It is all is possible to identify whether the function value, whether it is a minimum or a maximum value or inflected value, all these things we can identify. And we'll go for the next topic. There is a call it as a SWAM intelligence. So in a SWAM intelligence is our latest thing in term short form. SI, the SWAM intelligence, was introduced in 1989 by there is a Girdo Beni and other colleagues, and they published a paper also in this SWAM intelligence. Means using knowledge of collective objects or peoples. So this is the popular nowadays. All many optimization algorithms use with this approach only. What is this SWAM is meaning? Whether it is insects or animals or a people using, but the only thing is here knowledge of collective objects, or knowledge of collective insects, or knowledge of collective people or animals. Based on their natural approach, we are converting into problem, and we are finding the SWAM intelligence. Using the SWAM intelligence, we are going to find the optimal values. That's what means a group of objects. That object in general word, it may be people, or it may be insects, or it may be animals, or something like that. Let you can say problem statement to single person and tell him to him or her to go through this problem and then give a solution. Suppose if I ask to solve this problem to one person, then this means we will consider the solution of the particular person only. So if I assign the problem to you and I'm asking or expecting solution from you, that will be as a only particular person. But if the same problem is given to class or open-ended problem or any assignment, if I given to total group of people, all together they, if they solve, and then that is only nothing but as a SWAM intelligence, nothing else. Problem in the solution given by the person may not be the best solution, because only one person is only the intelligence, he can use it and he can solve, that may not be as a best or a good solution. So to avoid that, what we can do is the certain amount of people or SWAM or a group of people, and ask them to uh, solve the problem. Then what will happen? Computing all the respect together to reach as a best possible solution. This is the major difference you can think. What we can do is there is a problem. It may be real world problem or societal problem or anything, or complex problem or complicated problem. If I ask one person to solve, that may not be as a best solution. We are asking to find the group of people to solve that. That may be as a best possible solution. That's what I mentioned here. So what we can do is we are using the knowledge of group instead of using one person knowledge. The knowledge group of people knowledge will to reach the best solution or optimal solution for the problem. That solution will give as a individual also good for all of them individually, because everybody to learn through group of peoples, and idea behind this form is like this. That's only the The SWAM intelligence, each individual or object in a group, in a independent of others. Each individual is responsible for their own contribution to solve that problem. That is one what I'm explaining, trying to explain is here. Behind of this algorithms optimization, spam optimization algorithms, what is why it is so popular? Because here group of peoples together will work. They are independent to each other. They are trying to get their solution and they compare that solution with the other people and they learn from that and again they will update their knowledge and keep on doing this problem group of people. So whatever the final solution you are getting, that is your final optimal solution. So let's take an example. Collective knowledge of objective is better than an individual objective. So normally it is true for all the cases. Collective decisions will give you as a better solution than individual solution. Now you can see there is a just for example to understand why the statement is valid. One point I'm telling, there is a jar contain 500 marbles or some chocolates or small things. Uh, Anything, some items are small. The question is, without touching the jar, a person need to predict how many marbles are in the jar because there is a jar. It may consisting of some marbles. If one person is predict, if I ask same jar, if I ask one person how many marbles inside, he may give some answer. It may be 200 or 400 or 250 or 150 or anything randomly. He may say something. Whether you will expect that answer is correct, it is not at all possible. You can predict the exact answer. But now, what we can do is we'll ask more number of people. Suppose same jar, if I ask 1,000 people, then 1,000 people answers if you store it and take it as a average of that, then your answer must be very near to the actual answer. That is the power of SWAM or a group of people or objectives. So it is very near. Or another version also you can do. You collect the same information, 1,000 people, and the highest 10 percentage or 5 percentage of highest values and lowest values you discard and take average, then it is still better than what we did in the previous. That means your answer is very near to the actual answer. Actual answer is 500 marbles are there inside. Now, if 1,000 people, if we ask same question, how many marbles inside? They may say they randomly different answers. Somebody may say the 1,000 marbles, somebody may be 10,000 marbles, somebody may be 10 marbles only like that. If you consider all the data and you discard highest values, first 5% or 10 percentage of highest values you discard and then lowest values also you can discard 10 percentage of the lowest value, 10 percentage of the highest values. After ascending order, then you discard the highest values of 5%, lowest values of 5%. The remaining values you take it as average, then your answer is reaches very near to actually is a 500 answer. That's what I'm trying to say here. Now you can see I asked 10 people only, very few peoples. The data I presented here. Somebody, the first person, they say 400 and then 450, 550, and so on, different answers. What we can do is 10 peoples, you just take it as average of that. If I take average of this solution, then this average got it as a 484. What is your actual answer? 500. No, instead of 10 members, if you expand the persons more and more, then we can easily identify a still better answer. So if I ask instead of 10, if I ask 50 people, or 100 people, then you take average, it is very near. Or still you ascending, make this data in ascending order, you discard upper side, not in the order. The values has to be ascending order, and highest values you can discard, and lowest values you can discard. In between values, you take it as a mean, then you'll get as a still better solution. That's what I mentioned here from different persons. 480 values we got it. That's what the reduces to only 16 marbles as compared to the previous error. It was, if I ask one person, he may say only 100, but actually it's 500. That is the way we can able to. The main idea behind spam intelligence is to collect the knowledge of what is spam intelligence. The answer in the simple, you can see that this in our previous marble example, which is collecting the answer from the responses. The different objects are a group of people individually, and then computing all responses as a whole, then the results is the best fit our given problem. That's what we can consider. So here, with this approach, we have more optimized solutions for a given problem, and that is the reason why we call it as a spam intel. Because in this previous problem itself, the answer is not fixed one. The answer they said 484. If I take 10 people, the opinion. If I take 20 people opinion, then the average may be four. You got maybe 490, but still actually is 500. Then if I take 100 people, then your answer may be near to that, like that. That is what I mentioned is spam intelligence come into the picture, the most optimal solution it will give, but it is not a fixed solution. It is going to be vary with respect to other. So this is a small brief introduction about spam intelligence, and next class we'll see the next topic. By this end of this week, I'm trying to complete the first unit. These are very fundamental. From next unit onwards, there is a different optimization algorithms we need to use, and that you have to complete your problems. How better you can use your optimization algorithms and all, make use of this. So now we'll stop this. If you have any problem, you can. And I asked you to attend Saturday for mini project. Nobody came on this Saturday, so this Saturday you must attend for this mini project. Okay, thank you.